Yes, Nana. Put the heading alkanes, hydrocarbons. In hydrocarbons, we are going to discuss alkanes, alkenes, alkynes, alkanes, alkene, alkyne. So alkanes, Nana, general formula we are using CN H2N plus 2. Right, alkenes CN H2N. Next, alkynes H2N minus 2. Very good. Right, now alkanes, generally in case of alkanes, saturated hydrocarbons we could say. Saturated hydrocarbons. Saturated means carbon is having the 4 single bonds. In case of here is unsaturated, this is also unsaturated. Alkenes and alkynes. In case of alkanes, the 4 carbon is having 4 single bonds. Whereas in case of alkenes, one double bond will be there. In case of alkynes, triple bond, right? Ane, ene, ine. Next, CC single bond length 1.54 angstroms. CC single bond length, write it down. CC single bond length. Here is 1.34 angstroms. Right? It is 1.20 angstroms. 1.20 angstroms. When CC single bond length is somewhat more, Nana. Single bond, when double bond is automatically size is somewhat, in case of alkynes, very small. And CC bond angle 109 degrees 28 minutes. It is 120 degrees. It is 180 degrees. So generally, alkanes undergoes free radical substitution reactions. Free radical substitution reaction. Alkenes undergoes electrophilic addition reactions and free radical addition reactions. Alkynes undergoes electrophilic addition reactions. Electrophilic addition reactions. Write it down. So generally, it undergoes sp3 hybridization, sp2, sp carbon. Tetrahedral shape, trigonal planar, linear shape. Right? sp3 hybridization, sp2, sp. So generally, alkanes were called as paraffins. Alkanes were called as paraffins. Paraffins. Alkenes generally were called as olefins. These were called as acetylenes. Oily like substances, alkenes, that's why we could say olefins. Alkanes, less affinity, less reactive. So in electrophilic addition reactions, so in alkenes and alkyne, I told you, alkenes are more reactive. Alkenes and alkenes and alkynes, which one we can easily break the bond? Obviously, CC single bond. Yeah, bond length is inversely proportional to bond energy. In case of alkanes, nomenclature part, of course, we know, right? Alkanes nomenclature, right? Only one carbon, 4 single bonds, meth plus N, methane, right? Ethane, propane, right? Butane, pentane, hexane, condensed forms. So if you are writing, this is 1, 2, 3 carbons now, right? This is 1 carbon, 2nd carbon, 3rd carbon, 1, 2, 3. So C, C, C. Carbon is always having 4 bonds. So here is already 1 bond is there. Remaining bonds we are accompanied by, we'll write with hydrogens. So we can write like this, or this is the condensed form, CH2 CH3. This is the bond line formula. So anyway, we can write bond line formula, alkanes. So the first rules already we know. First Select the longest chain rule, right? I already explained. Select the longest chain rule, then least numbering rule. So where we want, what is the parent chain here? How many number of carbons? Parent chain is having how many number of carbons? Yeah. So here onwards, 1, 2, 3, 4, 5, 6, 7, 8. 4 methyl octane. 4 methyl octane. So 8 carbons means oct. All are single bonds. Ane. So at 4, 1, 2, 3, 4, 5th position it's coming. So least numbering rule also we included over here. For example, here is ethyl group is there, here is methyl group is there. So where we have to start the numbering? Ethyl, alphabetical order we need to follow. So 3 ethyl, 7 methyl, nonane. 3 ethyl, 7 methyl, nonane. For example, try to understand same question, Anna. Here is the ethyl group. Here is the methyl group. Okay. Now let me know where we have to start the numbering. Methyl. Why? Lowest. This is coming the second number. For example, 1, 2, third number is coming. So if both are coming in this case, what exactly happens? 1, 2, 3, 1, 2, 3. So both are same number. If it is coming, then we are following the alphabetical order. But in this case, it's the first 2 methyl. So 2 is now 3 ethyl, 2 methyl, nonane. Write it down. For example, the compound is given like this. So 7, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So now this one is what? This is the substitute vendor. Right, here onwards we need to start the numbering. 1 is 2, 3, 4. How we have to write the 7, bracket opens, 1, 2 dimethyl, 1, 2 dimethyl, butyl, tridecane. So 11 carbons undecane, 12 dodecane, tridecane, tetradecane, pentadecane, hexadecane, like that. Write one more. So least numbering is coming from this side, I think, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Tetradecane. Here onwards. 1, 2, 3, 4, 5. So 7, 1 comma 2 comma 3 comma 4 tetra methyl pentyl tetradecane. tetraecane. Write it down. Right, in case of isomerism, for alkanes, already we discussed isomerism. Alkanes undergoes chain isomerism, of course. Chain, right? Is this undergoes the chain isomerism? Propane. Is propane undergoes the chain isomerism? What is isomerism? Compounds which are having the same molecular formula but different in their chain structure, right? So this is won't participate because it won't show the chain isomerism. In case of butane, Nana? Yeah, this is N-butane. N-butane. This is isobutane or 2-methyl propane. Isobutane. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Write the chain number of chain isomers as a homework. I already discussed this. Which one? This one is pentane. N-pentane. Straight chain, whenever it's straight chain, we have to write N-butane, N-hexane. Is alkenes shows the position isomerism. So, minimum number of carbon atoms are required to show the position isomerism for an alkane. 1, 2, 3, 4, 5. Here is one, right? Total. What is this name? 1, 2, 3, 4, 5. 2-methyl pentane. Same if you are writing like this. In this case, what? 1, 2, 3, 4, 5. 3-methyl pentane. In this case, JN number is same, right? It is 51. 51 here is also 51. JN number. What is J? Parent chain. 5 carbons. Only one substituent is there. So N. 51, 51. So minimum number of carbon atoms for an alkane to show position isomerism is number of carbon atoms are 6. Numerical type of questions they are asking. Next, alkanes will show conformational isomerism. I already discussed in the conformational isomerism, when CC single bond is there, pre-rotation is possible. Pre-rotation is possible. What is pre-rotation? Imagine that this is carbon, right? Okay, carbon here. So free rotation means what? So now try to understand between this angle, we could say dihedral angle. Dihedral angle is 0 right now, or the same side, purple, this is blue, white. So now this is in the which form? If you are writing Newman formula, for example, the back side one, if I am showing like this. So here is, for example, methyl, hydrogen. From what you can take chlorine, something. 3 groups are there. Okay. Imagine this purple color ones are methyl groups. Okay. Methyl groups. This white color is hydrogen. And this blue color is chlorines, imagine. So right now, what exactly happens? This is in which form, Nana? Fully eclipsed. In case of fully eclipsed, 2 types of strains are possible. What are the 2 types of strains? Because of these groups, we could say the van der Waals strain or steric strain. And because of this bond, right? So because of this bond, this bond and this bond, Nana. Because of these bonds, we could say the torsional strain. Torsional strain. So if we are watching like this, you can see the front carbon, but we can't see the back carbon, right? So front carbon you can see, back carbon you can't. Got it? To avoid that one, so total It's how much degree angle? 120 degrees. So we are just moving this like this. CH3 Cl H. Here is what? CH3 H Cl. Okay. Now this is which form right now? So the back side one is, I'm just rotating like this. Now you can see, right? Gaussian form. So the Gaussian form means here, what I'm trying to say, the free rotation is possible. How many infinities means n number infinity structures we will get, because we will get n number of structures. Free rotation, when the carbon's free single bond is there, free rotation is possible. Got it? Hello. When double bond cases, in case of double bond cases, free rotation, triple bond cases, free rotation is not possible. They will show the geometrical isomerism. So now it is Gaussian form. For example, if we are rotating this bond to next one more 60 degree. So here you can say the CH3 over here, H, Cl. So one more time if you are rotating, you get staggered form. So here is the CH3, here is the hydrogen, in this case chlorine, this is staggered form. Staggered, or we could say anti. So this is what? Partial eclipsed. So partial eclipsed. So once again these structures are repeating, no? So every 60 degree angle we are rotating, we'll get the different structures. So which is more stable? I told you. Let me know. Staggered or anti or staggered? Then Gaussian. Then partial eclipse, then eclipsed. Eclipsed. This is stability order. Stability order. Right? Now, energy order is opposite. Energy is inversely proportional to stability. So energy order is what? Eclipsed, partial eclipsed, Gaussian, anti or staggered. Opposite. I told you two types of strains are there. Which strains? Torsional strain because of bonds, because of front bond and back bond, electrons repulsions are there. So those were called as torsional strains. Because of these groups, we could say van der Waals strain or steric strain. The exceptional case is there if the hydrogen bonding is possible. Gaussian is more stable than staggered. So if you want total full video, you can go and watch on our YouTube channel. So already it's optical isomerism is, I just uploaded. The same question live classes only is there. So still if you have any doubts, go back and watch the video, because I'm just revising here. CH3 H C2H5 H. Let me know which is more stable, Nana. CH3 H C2H5. Easy question only I'm asking. Easy question I'm asking. So this is staggered. Staggered or anti is more stable. Then this is eclipsed. In these two cases, let me know which is more stable. This is Gaussian. This is staggered. Yeah, let me know which is more stable. Obviously in this case Gaussian. Why? Here is hydrogen bonding is there. hydrogen bonding. When hydrogen bonding is there, the Gaussian is more stable than the staggered one. So write it on this. So not only here aldehyde we can take carboxylic acid, nitro group. So we know how the hydrogen bonding is possible. So if you don't know, let me know. I'll make one small video about the hydrogen bonding. Next one. Preparation of alkanes. Preparation of alkanes. Now onwards, alkanes, alkenes, alkynes, right? Benzene, haloalkanes, alcohols. So in all the chapters, first, the main thing is first introduction, nomenclature, isomerism, so then preparations, physical properties, chemical properties, and uses. So the main thing is, already we know nomenclature, so no need. Already we know isomerism, no need. So the important thing is preparations and chemical properties are important. Physical properties, so almost all somewhat easy only, but wherever it is important, I let you know. Because all physical properties, you know, it's see number of carbons, either they are gases or liquids or solids, what is its boiling point, what is its melting point, and how they are changing, increasing the molecular weight, so density, those things are there. I will discuss that. Preparations and chemical properties and uses are somewhat easy only. Generally they are not asking any questions based on uses, but according to general knowledge, why we need to study these alkanes, right? I'm asking you guys, why we need to study these alkanes, where we will use these alkanes. Let me know, anyone. Cooking gas, right? Whatever the cooking gas is there, because of that gas only we are eating every day, right? N-butane, isobutane mixture we are using the cooking gas, right? Without cooking gas, what happens? One day if the cylinder is completed at our home, if no delivery is nothing, so what we will do? In villages, no issues, they can use, right? The organic trees, those we can, but in Hyderabad, order cheskuntara, induction. Otherwise, Swiggy, Zomato is there, of course. Right. So lot of uses are there with the alkanes, right? So preparation. So the preparation first we'll discuss from alkenes. From alkenes to alkanes. Write it down. Preparation from alkenes to alkanes. Simply what we are doing now? Reduction. Reduction reaction in presence of nickel, platinum, palladium, right? Nickel, platinum, palladium, right? What exactly happens? Addition reaction takes place. Syn addition takes place. CH2H, CH2H. Syn addition means what? Same side, the hydrogens will attack. Same side. Even from alkynes also we will do the same reduction. For example, try to understand. Same side, thick line. Thick line means what? Same side. And towards observer. Towards observer. Dotted line means away from the observer. So we can write, or we can write syn hydroxylation. Syn hydroxylation means same. But here they'll ask one more question, right? What type of question they'll ask? If I am adding cis alkene, hydrogen, nickel or platinum or palladium, I am taking the trans, so here we'll get the stereochemistry. I told you cis. Hello, this is cis, right? This is trans. Cis and trans. This is which edition? In edition. In edition. TSR. TSM. M means what? We'll get. What we will get? Imagine, here is already put some. Here is some deuterium is there like this, right? CH3, hydrogen, deuterium. So this is which compound, Anna? Meso compound, right? Meso compound we will get. When it is trans, in addition, racemic mixture we will get. So imagine here also put DD. D means deuterium, because for identification process which I am telling, we are writing here. In isomerism topic I already explained. We'll get the racemic mixture is like this: hydrogen, deuterium, hydrogen. It is also deuterium, hydrogen, racemic mixture. Meso, what is meso? It is having the chiral center but optically inactive because in the presence of water. POS. What is POS? Plane of symmetry. So because if it is clockwise, this is anti-clockwise because of internal compensation. Optically inactive. So a lot of people nowadays lazy and they are doing the procrastination, right? And they want to do something. They are the dreamers. So in each person, three personalities are there, right? So what are those personalities? Dreamer, first dreamer. I want to do something. I want to become a IITian. I want to become a doctor. I want to become an IAS officer, and I want to buy this big house, Audi car, and so tons of gold, bank balance, like that. Dreamer, right? So one more person is there. So that is a person is critic. Always critic wants to protect. నువ్వు ఐఐటి అంటున్నావు కానీ ఫస్ట్ అయితే ఈ చాప్టర్ చదువు, నీకు అంత సీన్ లేదు, మర్చిపోతావు, సో యూ కాంట్ డూ దాట్, యూ కాంట్ దీస్ అని క్రిటిక్ చెప్తాడు. సో సెంటర్లో ఎవడు ఉంటాడు? ఇన్ ద సెంటర్ డూవర్. సో క్రిటిక్ డ్రీమర్ ఏం చెప్తున్నాడు? సో యూ వాంట్ టు డూ సంథింగ్ బిగ్ ఇన్ యువర్ లైఫ్. క్రిటిక్ ఏమంటాడు? అరే నీకు అంత క్యాపబిలిటీస్ లేవు, సో యు ఆర్ యావరేజ్ పర్సన్, అది లేదు ఇది లేదు. సో ఇప్పుడు ఏం చేస్తాడు డూవర్? రైట్, కన్ఫ్యూజన్కి వచ్చేస్తాడు. రైట్, చేయాలని ఉంటుంది కానీ ఇక ఈ క్రిటిక్ మాటలు వింటాడు. రైట్, ఏం చేస్తాంలే, అదంతా ఎంతో కన్ఫ్యూజన్కి వచ్చేసి ఇప్పుడు రైట్ ఇప్పుడైతే ప్రస్తుతానికైతే ఇన్స్టాగ్రామ్ సంథింగ్ ఏదో చేసుకుందాం, స్క్రోల్ కొట్టుకుంటుంటాడు. వాడికి చేయాలని ఉంటుంది, బట్ క్రిటిక్ ఉంటాడు. డూవర్ ఉంటాడు కదా, ఈ డూవర్ అనేటోడు. దీనివల్ల ఏంటంటే దే నో దట్ ఈస్ ఇంపార్టెంట్. మనకు కూడా ఎగ్జామ్స్ ఉంటాయి, ఈ ఎగ్జామ్లో టాప్ కొట్టాలని మనం అనుకుంటాం. అరే నీకు ఏం వస్తుందరా, ఏం రాదని క్రిటిక్ అంటాడు. ఇప్పుడు చదవాలని ఉన్నా కానీ ఏం చేస్తాం మనం? వి వోంట్ డూ ఎనీథింగ్. అర్థమవుతుందా? సో అప్పుడు ఏం చేయాలి మనం? ఈ కండిషన్లో ఏం చేయాలి? క్రిటిక్ మాట వినొద్దు కాదు, క్రిటిక్ మాట వినాలా. బట్ ఏం చేయాలి? క్రిటిక్ అనేటోడు మనకి హెల్ప్ చేస్తాడు, అంటే మనం సేఫ్ జోన్లో పెట్టడానికి ట్రై చేస్తాడు. నువ్వు సేఫ్గా ఉండాలా, నువ్వు ప్రాబ్లం ఫేస్ చేయొద్దు. నువ్వు ఫర్ ఎగ్జాంపుల్ అక్కడికి వెళ్తే ఫెయిల్ అయినావు అనుకో, అందరు చూసి నవ్వుతారు కదా, నువ్వు అవసరం లేదని చెప్పేసి లాట్ ఆఫ్ క్రిటిక్ చెప్తాడు. క్రిటిక్ చెప్పేది మన మంచి కోసమే, రైట్? కానీ క్రిటిక్ని మనం ఏం చేయాలి? 3 A's. అవేర్నెస్ చేయాలి, అప్రిషియేట్ చేయాలి. అవేర్నెస్ అంటే అసలు ఏం చెప్తున్నాడు క్రిటిక్ అనేది వినాలి. తర్వాత క్రిటిక్ని మనం అప్రిషియేట్ చేయాలి. తర్వాత మనం ఏం చేయాలి, అథారిటీ తీసుకోవాలి. 3 A's we need to come out from the critic, which is A. ఫస్ట్ అవేర్నెస్. క్రిటిక్ ఏం చెప్తున్నాడు, నిజమేనా, మనకు అంత సీన్ లేదా, రైట్? వాడు క్రిటిక్ చెప్పేది వినాలి. ఎందుకంటే ఇప్పుడు ఫర్ ఎగ్జాంపుల్ షిప్ చేస్తారా, షిప్ ఈజ్ సేఫ్ ఇన్ ద ఎక్కడ షిప్ యాడ్లో ఎక్కడ అక్కడ ఆ ప్లేస్లో సేఫ్గా ఉంటుంది. అక్కడ సేఫ్గా పెట్టడానికి షిప్ తయారు చేశారా? ఏరోప్లేన్ ఉంటుంది. ఏరోప్లేన్ ఎయిర్పోర్ట్లో సేఫ్గా ఉంటుంది. రైట్? అది ఎగిరితేనే కదా ప్రాబ్లం వచ్చేది. సో సేఫ్ జోన్లో ఉంటుంది. ఏరోప్లేన్ అంతా బిల్డ్ చేసి సేఫ్ జోన్లో పెడతామా, లేదంటే రైట్ ఫ్లై చేపిస్తామా? ఫ్లై చేయించాలి కదా. సో ఫస్ట్ ఏం చేయాలి, క్రిటిక్ని అవేర్నెస్, దెన్ అప్రిషియేట్. యు ఆర్ గుడ్, సో నువ్వు చెప్పేది బాగానే ఉంది, బట్ అథారిటీ తీసుకోవాలి. నేను సేఫ్గానే ఉంటాను, బట్ నేనైతే ట్రై చేయాలి, ఐ హ్యావ్ సమ్ డ్రీమ్స్ అని చెప్పేసి ఇలా ఫైట్ చేయాలి. ఇలా చేసినప్పుడు వీ విల్ కమ్ అవుట్ ఫ్రమ్ ద ప్రొకాస్టినేషన్ ఆర్ సంథింగ్. ఆల్కేన్స్లో ఫ్రమ్ ఆల్కీన్స్, ఈవెన్ ఫ్రమ్ ఆల్కైన్స్ ఆల్సో వీ కెన్ డూ నానా. ఫ్రమ్ ఆల్కైన్స్ C triple bond CH, రైట్? సో ఇక్కడ కూడా ఏంట్రా, ఆల్కేన్స్ కన్వర్టింగ్ ఇంటూ ఆల్కీన్స్, తర్వాత ఆల్కేన్స్ అయిపోతాయి. ఫర్దర్ రిడక్షన్, రైట్? ఫ్రమ్ ఆల్కైన్స్ ఆల్సో we can convert into alkynes. So alkenes and alkynes లో in hydrogenation లో alkynes are more reactive than alkenes. Nana, very important point. Alkynes are more reactive in than alkenes in hydrogenation. Hydrogenation means simply we are adding the alkenes, because this alkene is linear. Linear means what? So the hydrogens come easily, can attack alkenes. But in electrophilic addition reaction, so note, but in electrophilic addition reaction, alkenes are more reactive than alkynes. These 2 points just key note, very important. Clemmensen reagent. What is a Clemmensen reagent? Zinc amalgam in presence of concentrated HCl. Zinc amalgam, Hg we are called as amalgam. Zinc amalgam in presence of concentrated HCl. Otherwise we can use Wolff-Kishner reagent. Wolff-Kishner. Hydrazine, NH2, hydrazine in presence of base, OH minus, basic medium. Hydrazine in presence of base. Otherwise we can use HI in presence of red phosphorus. 1, this is 2, this is 3. Particularly aldehydes and ketones. Hello. Aldehydes and ketones. Any of these, 1 or 2 or 3. 1 or 2 or 3. What we will get? We'll get alkanes. Clemmensen reagent, Wolff-Kishner, hydrazine, this is hydrazine in presence of base, basic medium, this is acidic medium, HI in presence of red phosphorus is a strong reducing agent. Strong reducing agent, RA. So these compounds mechanism is there. First mechanism is not needed. First learn the reagents and what is the purpose and what is the reactant and product. Then afterwards I'll explain the mechanism. RC double bond O H. For example, zinc amalgam in presence of concentrated HCl. You'll get R CH2H. Means what? Simply we can write RCH3. CH2 C double bond O is converting into CH2 nana. C double bond O is converting into CH2. For example, CH3 C double bond O H, they are using the same zinc amalgam in presence of concentrated HCl, will get ethane. Write it down. If you can take ketone. So not only zinc amalgam in presence of concentrated HCl, we can take hydrogen in presence of base as well as HI in presence of red phosphorus. For example, C double bond O. We don't like this C double bond O. We want to remove. What we need to do? We don't want this C double bond O group. So we want to make like this. What we have to do? Any of these three reagents we can use. Write it down. Hydrogen, I'm using hydrogen in presence of base. Or right, zinc amalgam, concentrated HCl, or HI in presence of red phosphorus. Come on, write it down. How much bigger it would be, that doesn't matter. Come on, write it down. So there is one more important question, right? Here is somewhat so zinc amalgam, presence of concentrated HCl. Next, hydrazine in presence of base, HI in presence of red phosphorus. The main important thing is Clemmensen reagent. Clemmensen's reagent will reduce both aldehydes, ketones as well as alcohols also. So here what we will get generally cyclohexane. Whereas Wolff-Christian reagent won't reduce the alcohol. This is the important thing which we need to know. HI in presence of red phosphorus will reduce both. This is the 5-star one. So write it down. Wolff-Christian reagent won't reduce alcohols. So Clemmensen, Wolff-Christian, HI in presence of red phosphorus. Next now, decarboxylation. Decarboxylation. So we are using the decarboxylating agent NaOH plus CaO. They are called as what, Nana? Soda lime. Good. Soda lime. Or COOH, carboxylic acid. Generally, NaOH, acid base reaction takes place. So generally sodium salt of carboxylic acid generally we can take. Okay? Or COONA. If you are taking the carboxylic acid also, that is immediately converting because Neutralization reaction takes place, product is forming immediately, very instantaneous reaction. So sodium salt of carboxylic acid or carboxylic acid, doesn't matter. So if you're taking the carboxylic acid, that is converting into sodium carboxylate. A lot of people are confusing here. NaOH, PaO, calcium oxide. Here is what exactly happens now. This is going out. Na2TO3. This H is coming to attack this R, alkyl group. So we'll get RH alkane plus Na2CO3 is going out. Na2CO3. CH3, COONA, NaOH. Write the compounds. In this case, methane. In this case, ethane. This is going out of propane. We will get. You can take the benzene, we will get the benzene also. Come on, write it down. Byproducts is same, right? Next, coal-based electrolysis is there. Coal-based electrolysis, and tomorrow I'll do some more preparations directly, right? And physical properties, chemical properties we'll discuss. Okay? Okay, no? 8 o'clock. The remaining things we'll continue tomorrow. Thank you.